Do IDs have shape? What does have to do with deep learning? And how do we know that these are all dogs? Well, according to Plato, the world can be divided into two worlds: the visible and the intelligible. We grasp the visible world with our senses. The intelligible world we can only grasp with our mind. It is the world of abstractions or ideas. These ideas have an actual shape, which Plato called forms, and particular entities are simply shadows or imperfect projections of these forms. So according to Plato, we know that these are all dogs because there is an abstraction or ideal form called dog, and the particular dogs are imperfect projections of that form. What does that have to do with deep learning? Well, the main message of this talk is that artificial neural networks are essentially discretized solvers for a generalization of image registration variational problems. In this generalization, images are replaced by high-dimensional reproducing kernel Hilbert spaces, and while image registration seeks to align two images by matching material points via transformations of their coordinate systems, this generalization seeks to align RKHS spaces by matching data points. This identification allows us to initiate a theoretical understanding of deep learning from the perspective of shape analysis with images replaced by high-dimensional RKHS spaces, which Plato would have called forms. We will describe this theoretical framework by addressing the supervised learning problem of recovering an unknown function f dagger given f dagger of x equals y. We will assume that the input and output spaces are finite-dimensional Hilbert spaces. We write x and y for the n-dimensional input-output vectors whose entries are the input-output data points, and we write f dagger of x for the n-dimensional vector whose entries are the images of the input data points under f dagger. The artificial neural network solution is to approximate the target function with the composition of nonlinear functions which we write f1, ft. To define these functions, write x1 for the input space x, xt plus 1 for the output space y, and sandwich the spaces x2, xk, xk plus 1, etc. between the input space x and the output space y. And let fk be the function mapping the space xk to the space xk plus 1. For artificial neural networks, fk is typically the composition of a nonlinear activation function, which we write a here, with an affine function, which we write wkx plus bk plus 1. This activation function is typically an element-wise nonlinearity, such as ReLU, CeLU, or the hyperbolic tangent. The affine function is represented by the linear operator wk, mapping xk to xk plus 1, and the vector bk plus 1 of xk plus 1. So wk and bk plus 1 represent the weights and biases of the kth layer of the network, and these weights and biases are typically identified by minimizing some empirical loss defined as some distance between f of x and y via stochastic gradient descent. In this talk, we will focus on the variants of ANNs, achieving the state-of-the-art in industrial applications. These are the residual neural networks, known as ResNets, introduced by her and others to facilitate the training of very deep networks. The ResNet solution to our original problem is to approximate the target function f dagger with the composition of d functions, which we write capital F1, capital Fd. Each capital Fk, which we will call a ResNet block, is the composition of the function fk, mapping the space xk to the space xk plus 1, with the composition of lk functions, mapping xk to xk. Each lowercase fk is, as before, the composition of an activation function with an affine function, and each one of these lk functions is the sum of the identity operator and a function vk mapping xk to xk, obtained as the composition of the activation function with an affine function. And, as before, the weights and biases of all these functions are identified by minimizing the following empirical loss, which is a quadratic loss on the mismatch between f of x and y. As observed by Haber and others, the following function, appearing in each ResNet block, can be interpreted as a discrete approximation of the solution of the following ordinary differential equation / dynamical system, defined by the activation function A and some time-dependent weights and biases to be identified as before by minimizing some empirical loss on the mismatch between f of x and y. This interpretation opens the possibility of using ODE integration techniques for designing the underlying ANN. For instance, Haber and Ruturto proposed to restrict the previous class of ODEs to Hamiltonian ODEs and use symplectic integrators for their discretization to ensure stability. Chang and others proposed to use the following Hamiltonian system to ensure stability and reversibility. Now, to describe the image registration interpretation of ANNs and ResNets, I will first give a reminder of kernel-based solutions to our original approximation problem. Since the output space of the target function is not the real line but a vector space, we will need to employ vector-valued or operator-valued kernels. So our next step will be a reminder of operator-valued kernels. Operator-valued kernels were introduced by Kadri and others as a generalization of vector-valued kernels introduced by Alvarez and others. To describe these operator-valued kernels, let x and y be separable Hilbert spaces, and let L of y be the set of bounded linear operators on y. We say that a function mapping x times x onto the set of bounded linear operators on y is an operator-valued kernel if k of x, x prime is self-adjoint with respect to the inner product on y for all x and x prime, and if the following positivity condition is satisfied for all xi in x and all yi in y. We say that this operator-valued kernel is scalar if it can be written as the product of a scalar-valued kernel little k and the identity operator on y. So this little k is a mapping from x times x onto the real line, and it is a scalar-valued kernel. This operator-valued kernel defines a reproducing kernel Hilbert space of continuous functions mapping the space x to the space y, defined as the closure of the span of the following functions, where the span is taken over all x and y in x times y, and the closure is defined with respect to the following RKHS norm defined by the following reproducing identity. And we will use the following notations for the RKHS norm defined by the kernel K. Let F be a separable Hilbert space and psi be a function mapping the space X onto the space of bounded linear operators from the space Y to the space F. We say that F and psi are a feature space and a feature map for the kernel K if the following identity is satisfied for all x, x prime, and y, y prime, where this is the inner product in the space F. We summarize this identity by writing the following identity, where psi transpose is the function mapping the space X to the space of bounded linear operators from the space F to the space Y, and this psi transpose is defined by the following identity, where this is the inner product on the space F and this is the inner product on the space Y. Then we have the following theorem, which states that the RKHS space defined by the kernel K is the linear span of psi transpose alpha over alphas in the feature space F. And we also have the following Parseval-like identity, which states that the RKHS norm of psi transpose alpha is equal to the F norm of alpha. Now let us describe the kernel method solutions to our original approximation problem. The optimal recovery solution is to approximate the target function with the minimizer of the following optimization problem, which admits the following representation formula. In this formula, Kxx is the n times n block matrix with the following block entries, and K little x capital X is the 1 times n block vector with the following block entries. This optimal recovery approximant can be traced back in numerical approximation to the work of Micheli and Rivlin, and it is called optimal recovery because it is minimax optimal if the loss is defined as the relative error in the RKHS norm defined by the kernel K. Furthermore, we have the following pointwise error estimate that does not depend on dimension, but requires bounding the RKHS norm of the target function to be useful. The ridge regression solution to the original approximation problem is to approximate the target function with the minimizer of the following optimization problem, and this minimizer admits the following representation formula, which can be obtained from the optimal recovery representation formula by adding a nugget to the following block matrix, and this nugget is simply a multiple of the identity matrix. This ridge regression solution is minimax optimal in the setting of Tikhonov regularization / mode decomposition. And as with optimal recovery, we have the following pointwise error estimates on the accuracy of the approximation. Motivated by the structure of ResNets, let us now consider the variant of ridge regression in which we approximate the target function with the composition of a function f mapping the space x onto the space y and a deformation of the input space mapping x to x, which can be written as the composition of L functions, each one of them being written as the sum of the identity operator, and a displacement mapping the space x to the space x. This function f and these displacements vs are then identified as minimizers of the following optimization problem, where these are the RKHS norms defined by the operator valued kernels k and gamma, where k allows us to regress functions mapping the space x to the space y, and gamma allows us to regress functions mapping the space x to the space x. We will now numerically illustrate the deformation phi learned by the proposed approach, which we will call mechanical regression. In the following experiments, the dataset is the Swiss roll dataset. The dimension of the input space is 2 and the dimension of the output space is 1. The points xi have label yi equals +1 if they are red, and yi equals -1 if they are blue. These figures illustrate the deformation phi at different discrete times t by showing the image of the input dataset under the deformation phi at different discrete times. We can see that if nu is small, where nu is the penalization parameter on the RKHS norms of the displacements, defining the deformation via composition, then the Swiss roll unrolls. And if nu is large, then the unrolling of the Swiss roll is limited. In the following figures, we compare mechanical regression with ridge regression on a simple one-dimensional regression problem. The value of nu is +∞ for ridge regression, and we take the value of nu to be 0 for mechanical regression. The red curve on the left column shows the testing data, and the blue points on the left column show the training data, which has decreasing level of noise from top to bottom. Note that the input space is the interval 0, 1, and the output space is the real line. The center column shows the testing error versus the value of lambda. The blue curve is the testing error of ridge regression. The red curve is the testing error of mechanical regression. Note that the testing error of mechanical regression is significantly smaller than that of ridge regression over a large range of values of lambda. The right column shows in green the approximation obtained from ridge regression, and in red the approximation obtained from mechanical regression. The bottom right figures show the deformation learned from the data for different values of lambda. Despite their simplicity, these deformations have a large impact on testing errors. In the following figures, we use the MNIST and Fashion MNIST datasets. The left column shows the testing error versus lambda. The blue curve corresponds to ridge regression, and the red curve shows mechanical regression with nu equals 0. Observe that again, the mechanical regression testing errors remain below that of the ridge regression testing errors for a large range of values of lambda. The figures in the right column show phi of an image in class 5 for different values of lambda. The underlying kernels k and gamma used here are obtained from random feature maps. If we call this approach mechanical regression, then let us now show that ResNets are a particular case of mechanical regression with a carefully chosen kernel gamma and a carefully chosen kernel k. To see this, let gamma and k be scalar operator-valued kernels defined by the scalar kernel little k, having feature space the direct sum between x and the real line, and feature map var phi. Therefore, our scalar-valued kernel little k is of this form. In that case, we can see that f composed with phi l is of the following form, where this w tilde is a linear operator mapping the direct sum between the space x and the real line to the space y, and these WS are linear operators mapping the direct sum between the space X and the real line to the space X. If this feature map var is of the following form, where 1 is the constant function 1, which we can interpret as an always active neuron, and A is an activation function mapping the space X to the space X, which can be an element-wise nonlinearity, then this regressor F composed with phi L has the structure of one ResNet block, and these parameters W tilde and WS are essentially the weights and biases of that ResNet block. To summarize, if the kernels gamma and k are of the following forms, where I of x is the identity operator on the space X, and I of y is the identity operator on the space Y, and var phi is a feature map of the following form, where A is an activation function mapping the space X to itself, then F composed with phi L has the structure of one ResNet block, and mechanical regression is equivalent to regressing the data with one ResNet block with L2 regularization on the weights and biases of that block. Now let us return to our original mechanical regression solution, which is to approximate the target function with the composition of some function f mapping the input space X to the output space Y, with a deformation of the input space represented using L displacements mapping the input space to itself. And F and these L displacements are identified as minimizers of the following optimization problem, in which the RKHS norm of F and the RKHS norm of these displacements are defined using arbitrary operator-valued kernels k and gamma. Now we have the following theorem. As L goes to infinity, so recall that L is the depth of the network or the number of displacements defining the deformation of the input space. So as L goes to infinity, the adherence values of the mechanical regressor F composed with phi L are F composed with phi V, where phi V is the solution of the dynamical system with vector field V, and this F and this vector field V are minimizers of the following optimization problem, which looks like an image registration / computational anatomy versional problem. The kind of question that you try to answer in image registration, which is a branch of computational anatomy, is how to best align an image I with an image I'. And this is typically done by deforming the coordinate system of the first image to align it with the second image. This deformation is identified by minimizing the following variational problem, in which the first term is enforcing the smoothness of the vector field driving the deformation of the first image, and the second term is an L2 distance between the deformed first image and the second image. Now, there is a variant of image registration known as landmark matching, in which the L2 distance between the deformed first image and the second image is replaced by an L2 distance between material or landmark points on the first image displaced by the deformation, and material points or landmark points on the second image. The variational problem that we have obtained as a limit of mechanical regression looks like an image registration variational problem with landmark matching, with a few differences. The support of the images I and I prime is no longer the unit square, but it is the input space X for the image I and the output space Y for the image I prime. And those images are replaced by abstractions. The landmark or material points Xi and Yi are no longer points in the unit square, but they are data points living in the input space X for the input data points Xi and the output space Y for the output data points Yi. We are no longer deforming the unit square or an underlying image mapping the unit square to the real line, but the input space, which could be high dimensional, and an underlying implicit image mapping the input space X to the output space Y, which could both be high dimensional, and is typically an element of an underlying RKHS space. So therefore, we are implicitly deforming an underlying RKHS space. Let us call ID registration this generalization of image registration in which we deform the input space with phi and then map that deformation to the output space with the function f. Let us call ID registration block the composition of the function f with that deformation phi. Then we can evidently compose these ID registration blocks by mapping the input space to a sequence of spaces layered between the input and output spaces. So in this figure, we first map the input space X to the space X2 with the function f1. The space X2 is deformed with the flow phi2 and mapped to a space X3 with the function f2, which is itself deformed, etc., until we reach the output space Y. If we call ID formation this composition of ID registration blocks, then we can show that INNs and ResNets are essentially discretized solvers for ID formation problems, and CNNs are discretized solvers for ID formation problems with a particular choice of kernels for gamma and k, which we will call REM kernels. And I will cover those kernels later in this presentation. These results are obtained from the fact that ID registration is the limit of mechanical regression, and one ResNet block is a particular case of mechanical regression. We will now focus the presentation on ID registration, i.e., the following optimization problem, its minimizers, and the corresponding regressor of the target function. The Bayesian interpretation of this regressor is that it is a map estimator for the following stochastic process given the following information, where Xi is a centered Gaussian process with covariance function k. Phi is the solution of the following dynamical system in which the vector field is a centered Gaussian process defined by the following norm. This centered Gaussian process is independent from Xi, and Z is a centered Gaussian vector independent from zeta and Xi with ID n0 identity entries, and this is the identity operator on the space Y. Now, if this kernel gamma has feature map psi and feature space f, so this psi is a function mapping the input space x to the space of bounded linear operators mapping the space y to the feature space f, then this center GP defined by the following norm has the following representation, where the EI form an orthonormal basis of f, and this BI of t are IID one-dimensional Brownian motions. Therefore, their derivatives are IID white noise. Let us call deep residual Gaussian process the solution of the corresponding dynamical system with vector field zeta. Then this deep residual Gaussian process is essentially a continuous variant of the deep Gaussian processes introduced by Demianu and Lorentz, and it is closely related to the Brownian motion in the diffeomorphism group introduced by Baxendale and to the stochastic flows covered by Kunita. Now, ID registration is essentially ridge regression with a warped kernel learned from data. And this can be seen by observing that the following two regressors are equal. The first one is the ID registration regressor, obtained as the composition of F with Phi. The second one is a ridge regression regressor, obtained with a kernel KV that is equal to the composition of the kernel K appearing in ID registration with the flow map of the vector field V minimizing this ID registration variational problem. Warping kernels are not new. They were introduced in spatial statistics to enable the non-parametric estimation of non-stationary and anisotropic covariance structures. They were used in numerical homogenization to approximate the solution space of elliptic PDEs with rough coefficients. Their RKHS flow map version was introduced in kernelflows to learn non-parametric kernels from data via a variant of cross-validation. What you see in this video is the flow learned by the kernel flow algorithm for the Swiss roll dataset. Interplays between diffeomorphic transformations and learning have also been studied by Younes, Rousseau-Fablé, and Zamit and Mangione and others. Another equivalent perspective on what we have learned so far is that ID registration is Gaussian process regression with a Gaussian prior learned from data. This identification provides a mechanism for the extreme lack of robustness of ANNs with respect to data poisoning or adversarial noise. This mechanism is that of the extreme lack of robustness of Bayesian inference with respect to perturbations in the prior. Another cause of the extreme lack of robustness of ANNs is the fact that the flow map Phi is driven by a chaotic dynamical system, which is something that we will cover later on. I also refer to the recent work by Hansen and others on why instability is inherent to deep learning. So, an important question is, can we fix this lack of robustness? The answer is not without giving up some accuracy. because robustness and accuracy are conflicting requirements. So how do we fix it? Well, the image registration strategy, which we generalize to ID registration, is to simply add a nugget that is a multiple of the identity matrix to the kernels gamma and k. This regularization strategy is also the one that is commonly employed in geostatistics to regularize kriging. Adding this nugget does not change the functional form of the regressor, but it does change how f and v are identified at training time. The impact of these nuggets is to modify the ID registration variational problem so that the propagation of the training data does not follow exactly the dynamical system with vector field v. This is done for the kernel gamma by adding the trajectory of the input dataset to the ID registration variational problem and penalizing the difference between q dot and v of q. Similarly, a nugget is added to the kernel k by introducing the variable y prime and penalizing the difference between f of q1 and y prime. The same strategy can be employed for the regularization of mechanical regression and therefore for the regularization of ANNs. In the setting of the training of one ResNet block, this regularization strategy does not change the functional form of the ResNet block at training time, but it changes how weights and biases are identified at training time by introducing penalized errors on how the input data propagates through the layers of the network. And this regularization strategy leads to a network that is provably robust in the sense that the regressor is continuous in all variables, those variables being the training data and the input data. Therefore, this strategy provides a principled and rigorous alternative to dropout that is the natural extension of how kriging and Gaussian process regression are regularized in spatial statistics. The following diagram illustrates this regularization strategy for one ResNet block. So again, the functional form of the regressor does not change, but the propagation of the input training data is corrupted through the addition of these slack variables z1, z2, z3, zs, etc., whose norms are penalized in the training variational problem. And as with dropout, these variables only corrupt the propagation of the training data. Once we have identified the weights and biases of the network, they disappear at testing time. We will now characterize the minimizers of mechanical regression and ID registration variational problems. Starting with mechanical regression, we have the following theorem. The minimizer V of the following mechanical regression variational problem admits the following representation formula. In that formula, QS is a trajectory in data space formed by the transformation of the input training data as it propagates through the layers of the network. Gamma of QS is the n times n block matrix with the following blocks. Gamma dot of QX is the 1 times n block matrix with the following blocks. Q1 is equal to the input training data X, and the trajectory formed by the states Q1, Q2, QL plus 1 is a minimizer of the following discrete list action principle. Once we have identified a discrete list action principle, we can apply classical results from discrete mechanics. First, introducing the following momentum variables Ps, we obtain that the trajectory of QSPS follows the following discrete Hamiltonian dynamic. This implies that F and the Vs are uniquely determined by the initial momentum of this discrete Hamiltonian system, In particular, the weights and biases of L2 regularized ANNs are uniquely determined by the initial momentum of this discrete dynamical system. Therefore, as in image registration, one could use geodesic shooting to train the weights and biases of an artificial neural network. By geodesic shooting, I mean that the search of minimizers Vs and F to the mechanical regression problem can be reduced to that of an initial momentum, which in the setting of ANNs is equivalent to reducing the search of all weights and biases of the network to that of the weights and biases of the first layer of the network. Furthermore, as in image registration, the moment representation of minimizers is sparse, and the following figures illustrate this point for our previous Swiss roll dataset example. More precisely, this figure on the top right shows the norm of the value of the initial momentum as a function of I, where I is the label of the input data points. Furthermore, as a corollary, the near energy preservation of the minimizer of the discrete least action principle implies that the norms of the minimizers Vs or the norms of the weights and biases of one ResNet block after training with L2 regularization fluctuate by at most 1/L across the layers of the network, where L is the number of layers in that network. We have similar results in the continuous time setting. First, a minimizer V of the following ID registration problems admits the following representation formula, where Q is a trajectory in input data space Xn, starting from the value X and minimizing the following least action principle. Therefore, if we introduce the following momentum variables, then V is proportional to that momentum, and the position and momentum pair QP follows the flow of the following Hamiltonian. This implies that V and F are uniquely determined by the initial value of that momentum P0, and the RKHS norm of V is constant over the time interval 0, 1. If psi is a feature map for the operator-valued kernel gamma, and if we rescale the momentum variables by the number of data points, then the previous Hamiltonian dynamical system is equivalent to the following one, in which alpha is a trajectory in feature space that is amenable to mean field limit analysis. Note that the representation of a minimizer V of the ID registration variational problem separates into a product of a function depending only on X and a function depending only on time. The function depending only on X is the transpose of the feature map, and the function depending only on time is this function alpha of t, defining a trajectory in feature space. And we have the following theorem characterizing the hydrodynamic limit of the empirical distribution defined by position and momentum variables. These results are different from the ensemble analysis of gradient descent of May, Rotzko, and Van den Eyden in the sense that we are not characterizing how weights and biases evolve when minimizing an empirical risk via gradient descent, but what the minimizers of that empirical risk are when we add L2 regularization in the weights and biases. Now let us proceed with results on the existence, uniqueness, and convergence of minimizers. So, minimizers of mechanical regression and ID registration exist. Minimizers of mechanical regression and ID registration are unique up to the initial momentum P1 or P0. The minimal value of mechanical regression converges as L goes towards infinity to the minimal value of the ID registration variational problem. The adherence values of phi L obtained from mechanical regression are the phi V obtained from ID registration. And as a remark, minimizers of mechanical regression and ID registration variational problems are, for pathological examples, non-unique. This non-uniqueness is related to the notion of conjugate points in classical mechanics, which I will now illustrate with the following example. Assume that you have a pendulum in the 2D plane, initially at rest, and you want to apply an initial momentum so that the pendulum reaches an upside-down position with zero momentum once it gets there. Well, there is no unique solution to that problem, since you can give an initial impulse towards the right or an impulse towards the left. Finally, as in ridge regression, we have the following deterministic error estimates for ID registration, where Kv is the kernel K warped by the deformation phi V. Although these estimates do not depend on dimension, they require bounding the RKHS norm of the target function to be useful. And this is the hard problem to be addressed if we want to show that the curse of dimensionality can be alleviated. Now we can view mechanical regression and ID registration as a block in which we plug in the input training data capital X, the corresponding labels capital Y, the input little x, the initial momenta p0 and z, and we get the functional output little y corresponding to the input little x. And p0 and z are identified by minimizing a total loss written as the sum of the empirical loss, the deformation loss, and the loss corresponding to the regularity of the function f. Evidently, these mechanical regression and ID registration blocks can be composed. Composing mechanical regression blocks with the right kind of kernels lead to ANNs and ResNets. Let us call the ID formation the composition of ID registration blocks. Then it can be shown that ANNs and ResNets are essentially solvers for discretized ID formation problems, and CNNs are solvers for discretized ID formation problems defined with the right kind of kernels called REM kernels that will be introduced shortly. This can be shown by generalizing all the previous results on mechanical regression and ID registration to the composition of mechanical regression and ID registration blocks. Some of these generalized results are as follows. L2 regularized INNs/ResNets/CNNs have minimizers. These minimizers are uniquely determined by the initial momentum, which corresponds to the weights and biases of the first layer of the network. The norms of the weights and biases of ResNet blocks are nearly preserved across the layers of that block. ResNets converge to nested ID formation variational problems in the sense of adherence values as the depth of those ResNet blocks goes to infinity. We will now describe the kind of kernels to be used in ID formation to recover and generalize convolutional neural networks. These kernels, which we call REM kernels or reduced equivariant multi-channel kernels are built upon a generalization of equivariant kernels introduced by Reisert and Burkhardt. To present this generalization, I will first give a short reminder of equivariant kernels. So let X be a separable Hilbert space and let G be a group of linear unitary transformations acting on X. We say that an operator-valued kernel K mapping X times X to the set of bounded linear operators on X is G equivariant if the following identity is satisfied for all X, X prime, and for all G and G prime. Similarly, we say that a function f mapping the space X to X is G equivariant if the following identity is satisfied for all X and G. Writing e.g. for the expectation with respect to the R measure on G, we have the following proposition. Given a possibly non-equivariant kernel K, mapping the space X times X to the set of bounded linear operators on X, the following kernel obtained by averaging the kernel K with respect to the action of the group is a G equivariant kernel mapping the space X times X to the space of bounded linear operators acting on X. Furthermore, if K is scalar and weakly invariant in the sense that Kx prime is equal to K of Gx prime for all X, X prime, and G, then a function f having minimal K norm subject to f of x being equal to y and f being G equivariant admits the following representation formula, which is equivalent to kriging the data with the G equivariant version of the kernel K. Now let us cover reduced equivariant kernels. Let X be a separable Hilbert space. Let P and R be linear projections mapping X to X. Let G be a group of linear unitary transformations on X. G, P, and R can naturally be extended to powers of the space X as follows. Let C1 and C2 be two natural integers, and let K be an operator-valued kernel mapping Px to the power C1 times Px to the power C1 to the space of bounded linear operators on R times x to the power C2. Then we define KREM, REM stands for Reduced Equivariant Multichannel Kernel, as the operator-valued kernel mapping x to the power C1 times x to the power C1 to the space of bounded linear operators on x to the power C2, obtained by projecting and averaging the kernel K as follows. Now let us consider the situation where the kernel K admits the following feature map var-phi, where A is an activation function. Then the REM kernel obtained by averaging and projecting the kernel K has the following feature map psi, mapping x to the power C1 to the following feature space, which is the set of bounded linear operators from P times x to the power C1 plus the real line to R times x to the power C2. Then for W in that feature space, the product between P transpose of X times W can be written as the following expression, which involves a projection step and an averaging step with respect to the action of the group. This expression appears in the representation of any given layer of the regressor obtained from mechanical regression or from the composition of mechanical regression blocks. To illustrate this expression, consider the case where X is the space of 10 by 10 grayscale images with periodic boundaries. Take G to be this group of translations acting on that set. Take P to be the projection on the following 3 by 3 sub-image, and take R to be the projection on that 1 by 1 sub-image. The second column shows the action of the group element G' on the image X, and the third column shows the action of another group element G on the image X. And the bottom row shows the action of the projection P before translation, after translation with G' or G. Observe that translating the image X by G, then projecting that translation by P, is equivalent to translating the range of the projection P and then performing this projection. Therefore, the averaging and projection operators appearing in the representation formula of the product between psi transpose and W lead to a convolutional operation that is identical to the one used in CNNs. And if we compose mechanical regression blocks with such reduced equivariant multi-channel kernels, then we recover convolutional neural networks and their generalization. In this generalization, the pooling via striding operation commonly used in deep learning is equivalent to subgrouping operation. As a last remark, the minimizers of ID formation problems obtained with REM kernels can be represented by the Hamiltonian flow of these kernels, and the computation of these flows require performing convolutions on both images and momentum variables which live in the same space as images. To finish, the following list of references is relevant to this presentation, which is based on the following publication. And to conclude, let's return to our original question. Do IDs have shape? Well, the etymology of the word ID is mental image or picture, because this etymology can be traced back to Plato's view that IDs have a form or a shape. In that sense, it is quite intriguing that ANNs can be interpreted as image registration algorithms trying to align high-dimensional shapes, which we could call mental images.